Okay, this is your last video for Gen Chem 1. This is Chapter 10, Properties of Gases. Learning goals as usual. Master the ideal gas equation. Now, I'm going to ask you to be able to derive most of the other gas laws from that equation. And so I'm not going to give you all the equations because I really want you to learn how to just manipulate the main gas law, ideal gas law, to get the others. And that'll come in handy later. Um, But I'll give you the equations for like Graham's law of effusion and Dalton's law of partial pressure, which can't be derived from the ideal gas equation. Understand from a conceptual basis what the kinetic molecular theory of gases is. We'll do some stoichiometry, and that'll really be the same thing you've always done with, mass of A to moles of A, moles of A to moles of B. The only difference is you might be asked to calculate the volume of a gas produced. And if that's the case, once you get the moles of gas, you just use the ideal gas equation to get its volume. And we'll also be calculating the density of gas mixtures as something that can also be derived from the ideal gas equation. So if you get comfortable with that equation, you can go a long way to solving a lot of gas law problems. So here's the chapter. You'll notice that section 1010 we won't cover, and 1012. One is real gases. I think that's 1012, and 1010 I think is Henry's law constant. We never cover these typically in Gen Chem. There's not enough time. Most of you know the simple properties of gases. They don't have definite shape nor definite volume. They'll just fill any container. They mix completely with other gases. They're much less dense. The distance of separation between gas molecules is huge. The interaction between individual gas molecules is incredibly small compared to liquids and solids. Those types of things are pretty common to us. So these are their parameters affecting gases. And if you're familiar with the lab, then you recognize this. This is something that is done in lab where you get to look at these different parameters. And obviously, we'll talk about each of these as we move through the chapter and define them. We all know what moles are, we all know what temperatures, we all know what volume is. I'll really only address pressure. So, kinetic molecular theory. What this says is that gas molecules basically have tiny volumes compared with their container's volume. They don't interact with other gas molecules. And by saying these tiny volumes, it means basically it's mostly space, a gas. They move randomly, but constantly. A gas molecule is not going to stop moving. They engage in elastic collisions with the walls of the container and other gas molecules. And what we mean by when we say elastic collisions, we mean that the energy is conserved within that collision. So, for instance, if two gas molecules collide, one's moving fast and one's moving slow, the fast one might slow down after the collision, but that slow moving one will speed up to the same extent that fast one slowed down. So that there's no loss in energy for the most part from these collisions. And if they collide with a wall, then they maintain that energy as they bounce off that wall or the container heats up from that collision. They have an average kinetic energy that is proportional to the absolute temperature. And we say absolute temperature, it means basically we got to make sure we're using the Kelvin scale here, okay? And then it's proportional. If you don't use the Kelvin scale, it's not going to be proportional the same way. So you need to realize that. So here's a graph of one of the concepts that comes out of kinetic molecular theory. And kinetic energy is 1/2 mv squared. You learn that in physics or some sort of physical science course you might have had in high school, but if not, you know now that 1/2 the mass times the velocity squared is what the kinetic energy of a molecule is. It's the energy of motion as opposed to potential energy, which is stationary motion or stored energy. And what you notice here is that the particle speed versus the fraction of the particles, the lightest gas, which is going to be hydrogen, obviously has a greater speed on average. It still covers the entire range, but its average speed is much greater than oxygen, which is much heavier. So the lighter the gas, the faster it moves, and that's not rocket science. You might have guessed that. You might have known that already. Now let's talk about pressure. What exactly is pressure? Pressure is force per unit area. Okay, so atmospheric pressure is the pressure exerted due to gravity acting on the air above the Earth's surface. So literally, you have a column of air, that's accelerating towards the Earth due to gravity, and that's what pressure is. And there's different units of pressure. One thing it's nice to commit to memory is that 1 atmosphere is 760 millimeters of mercury, which is also 760 torr. They are equivalent. And when we say millimeters of mercury, we mean the height that a mercury column rises to is 760 millimeters. That's equivalent to 1 atmosphere. And I'll show you what I mean by that here in this next figure. So we usually say that atmospheric pressure is right around 1 atmosphere. Now it varies, of course, but that's pretty standard. At sea level, it's 1 atmosphere, which means a height of mercury would rise in atmospheric pressure 760 millimeters. That's all. That's what that means. And of course, that's 76 centimeters. And you can picture a meter stick. That's 3/4 of a meter stick, so it fits nicely in a room. You can make a barometer out of a liquid that's less dense than mercury, but if you made it out of something like water, you'd have to have a 33-foot barometer. So that's why mercury is used. It's nice and dense. But what is effectively happening here, this atmospheric pressure is right here, and it's pushing down on this mercury column like this. So as a result, it's going to push the liquid up the column. However, there's another opposing force, and that is the weight of the mercury column as a result of gravity. So the mass times gravity is what weight is equal to. You don't need to know that. It's a physics kind of topic, but you should be aware of that's what gravity is. That's what weight is. It's the mass of an object times the acceleration due to gravity, which is, of course, 9.8 meters per second squared. So the column stops rising when these two forces have kind of equalized each other. So if initially I put my barometer from, say, a vacuum out into sea level area of 1 atmosphere, it's going to push up. It's going to keep rising and rising and rising until it gets to here, because now the weight of the column is pushing it down, and that force exactly balances the force of the atmospheric pressure. So that's what atmospheric pressure is and where it's coming from. And of course, elevation is going to affect atmospheric pressure, because as we realize is the higher you go up, if you will, you got less air sitting on you. So at Everest, it's only 0.35 atmospheres, hence the problem, obviously, that you can't, breathe for long at the top of Everest, and most mountain climbers that go there use oxygen. There's been a handful that haven't. The air is so thin, we say, and obviously if air is 21% oxygen, but the air's thinner at Everest, that means obviously there's much less oxygen up there. Sea level's 1 atmosphere. Even Mile High Stadium is about 0.83 atmospheres in Denver. So, you always hear about, athletes have trouble if they, haven't trained in low altitude when they go to play in Mile High Stadium. So here is the ideal gas equation. What I want to show you here is how you can derive all the other equations, and then we'll go through those pretty quickly. So here's PV equals nRT. Now, let's imagine, we'll do Boyles Law first, a simple one. Let's imagine that we have a P1, a P2, a V1, and a V2. Means we have an initial pressure and an initial volume. And then we change the pressure, and the volume is going to change proportionally. And everything else is held constant. Okay? So if this is constant here, that doesn't change when I change from the P1 parameters to the P2 parameters. Let's just say I have 1 atmosphere initially, and I have 1 liter. And then I increase it to 2 atmospheres. Now you might have learned in lab that the new volume would be half of that, 0.5 liters. Well, this is still constant, which effectively means that P1V1 equals P2V2. That's the idea, is that this is constant. You can set these two equal to each other because they're both equal to this constant. R, of course, is the ideal gas constant we'll define later. T is temperatures, N is moles. So let's take another example. And you can do this now with any scenario. So there's no reason to memorize all these different equations. Let's say we have an initial We say we have initial volume of 1 liter and an initial temperature of 200 200 Kelvin. Okay. Now, actually, let's actually do pressure better because VT is already done with Charles' law. You'll see in a second. So let's stick with this. Let's say we have an initial pressure of 1 atmosphere and we're at 200 K. Now we're going to increase the temperature to 400 K. The new pressure is going to be double that. But what you can see to solve that, let's say it wasn't very simple like that and you want to solve it, what you do is you put everything that is not constant on one side of the equation. So what I'm going to do is bring temperature over here. So I'm going to wind up with P over T is equal to NR over V, which is now constant because I'm not going to change the volume. It's the same number of moles of gas, and R is always a constant. So now you have PT equals a constant. So what you can do is write a new equation. P1 over T1 equals P2 over T2. You can now solve for T2. Now we can know by looking at these numbers, if you double the temperature, the pressure is going to double. When they're on opposite sides of the equation, which means they're going to be directly proportional. That means if you increase one, the other one has to increase in order for the equation to still work, right? But for P and V, they're on the same side of the equation, so they're inversely proportional. We're on the same side because as you increase P, the volume must decrease, right, over here in order for this to still equal the constant. That's the key here. But when they're on opposite sides of the equation, like pressure and temperature, they'll be directly proportional instead of inversely proportional. And from this, now, you can now derive any equation you want. You can even have 3 parameters. You can have, for instance, let's say the number of moles is going to change too. So we're going to have P over NT is equal to R is equal to the constant, which is equal to RV in this case. Or I'm sorry, R divided by V. So you can see you can do whatever you want. And there's no name necessarily for this equation. We have Boyles and Charles and combined and Avogadro's. But there's more than just that. You can devise any one you want. You can have all 4 parameters on one side. So that's the way the questions will read. You'll be given a bunch. So here's Boyles Law. I'm going to go through these quickly. P1 equals V1. These are going to be inversely proportional. And they're not linearly related either. Pressure is linearly related to 1 over V, but pressure and volume are not, because you can imagine as the pressure gets higher and higher, you get to a point where you can't compress the gas much more, so you get this exponential effect approaching the asymptote there and not ever hitting the axis, because you can't have 0 volume. So you actually cannot have a linear relationship, because that would suggest that the volume would go to 0 at some point. And that's impossible. But otherwise, Boyle's law is just the one P1 V1 equals P2 V2. Charles' law is V1 over T1 equals V2 over T2. Here you can see it is linear, but it has to be in Kelvin. And you also notice that 0 Kelvin is negative 273 degrees C. This is really a theoretical temperature because you can't ever reach 0 Kelvin, because theoretically that would mean that the volume of the gas would be 0, which can't be the case. The gas molecules would have to stop moving for that to happen, to have 0 volume, 0 pressure. So this is a theoretical temperature only, but it is equated to negative 273 Celsius. Avogadro's law then is going to be the one that relates volume to moles of gas. And there's really nothing more to say there. As the number of moles increases, the volume increases proportionally. You can also think about all of these laws in terms of kinetic molecular theory, which is something you should do in terms of understanding the conceptual stuff. You might realize that as the number of moles increases, the volume has to increase if my temperature and pressure are going to remain constant, you see? So if you kept the same volume, the pressure would be increasing because you'd have more collisions. You think of pressure as collisions with the walls. So the number of collisions and also the speed of those collisions, what gives gases their pressure, if you will. So you might say too, also as temperature increases, the volume must also increase. Otherwise, the pressure would increase. You wouldn't be able to keep pressure constant. So that's the way to think about it from kinetic molecular theory, and that'll come about from your reading. Then ultimately, you can get this combined law because we've now, and this comes from all of these. We said that PV is equal to constant, VT is a constant, and V over N is a constant. You can combine these and now say that P times V over N and T in denominator here is equal to a constant. So I do is just combining these. We call this the combined gas law. Then you can also say, hey, if your number of moles of gas is constant, you can bring that over here. You can wind up with P1V1 over T1 is equal to P2V2 over T2. So by always grouping anything that's constant, and how do you know something's constant? Well, when you read the problem or the question, or if you're doing a lab, anything that's not changing is constant. So when you do the lab on gas laws and you have a syringe and that syringe is sealed, the number of moles of gas is the same all the time. And if it's held at room temperature, then the temperature is the same, so you know it's the same, and the other things are changing. So that's all you're doing is you're going to combine those two. Combined anything that's constant on one side of the equation and anything that's changing on the other side, and basically you can derive any equation from these four parameters. Something else you need to get familiar with is standard temperature and pressure, and I introduced this in the thermodynamic equation, but in the thermodynamic chapter, sorry. But it's a little bit different for gases. I think in thermodynamics it was 25 degrees C. Now it's 0 degrees C. And 1 atmosphere, that's the same, I believe. And the idea here is that for 1 mole of an ideal gas at STP, just using this, and I'll implore you to actually solve this, put in your temperature of 273, put in 1 for a mole of gas, put in your R constant, which we haven't defined yet, 0.0821 liter atmospheres per mole Kelvin. That's the one you'll use for ideal gas calculations. You'll learn to use the other value of R for some of your thermodynamic calculations. And put in 1 atmosphere for pressure and solve for the volume. You will get 22.4 liters. The important thing to realize here is that this is independent of the density of the gas. It doesn't matter if it's CO2, methane gas, oxygen gas, nitrogen gas. The answer is the same. Why? Well, we'll look at the equation. There's nothing there that defines the gas. There's no molar mass in the equation, which is us saying that basically the mass of the gas is irrelevant. The size of the gas molecule is irrelevant simply because gas is mostly space. And even though you can take a large organic gas and still calculate the volume and come up with 22.4 compared to a small gas like hydrogen, it's because the gas is mostly space. And the mass of the gas and the size of the gas molecule is irrelevant. Now, when you get to extreme conditions, which your end of your chapter talks about real gases and under situations where they do interact, so at higher temperatures and pressures, then the ideal gas law falls apart. You can't use it. But we're not going to deal with real gases. We're only going to deal with ideal gases. And for many cases in the natural environment, that's fine. We don't have any situations like that. I mean, of course, under industrial applications and certain conditions where gas is under high pressure, then things do change and you can't use the ideal gas equation. Okay, the next thing we're talking about here then is density of gases. And once again, we can derive this equation from the ideal gas equation. And your book goes through something. I think they make it a little bit more difficult than it needs to be. If you were given some parameters, let's say you're given some of these parameters, you're given, you always know R, let's remember that. Let's say you're given the temperature and number of moles of gas, and they want to know, what the density of the gas is. Well, you know density is mass per unit volume. And from this, you should say to yourself, okay, it's basically quantity of material over the volume of the gas. Okay? So, I'm sorry, I didn't mean to say density here. I didn't mean to say moles here. I meant to say you have pressure here. And you might reason from this to say, well, for me to get to density, I'm going to need to get the amount of material over volume. So I'm simply going to take V and bring it over here and make this N over V, right? And then I'm going to bring the RT over to this side. And you're going to wind up with P over RT is equal to N over V. Okay? And that's going to lead you to density. Now, it can't give you density. You would need to be given additional information. But one thing you always have at your disposal is to realize molar mass. And if you look at units, you can realize that N, which is moles, is equal to the mass of a gas divided by its molar mass. If you will, grams divided by grams per mole, right? Moles comes up here because 1 over moles is moles. The units of that is moles. So I can see where I'm going with this. And we'll do some example calculations in class. If you're given the mass or the molar mass, we can actually get to density. Ultimately, you can derive an equation here now if you rearrange this that says that Pm for molar mass over RT is equal to M over V, which is equal to density. And that's what we'll do in class. Density of gases are also often given in grams per liter because for liquids you use grams per cubic centimeter. That's a little bit small for gases, so we use grams per liter because they're not very dense. And hang on to this idea. We'll talk about this in class and do some calculations with that. One of the last things in the chapter then are these stoichiometric calculations, and this video is getting long, but basically this is no different than what we did before. We're going to be dealing with A plus B going to C plus D, and in some cases we're going to have one of these being a gas. And we're still going to use these mole-to-mole ratios, but ultimately if we're asked for like what amount of gas is being produced, we're actually going to have to go into PV equals nRT. And once you calculate the moles, you'll probably have been given a pressure, a temperature, and a volume, or something along those lines. You'll be able to calculate the volume. I'm sorry. Usually what you're after is that kind of volume. So you'll be given the pressure and the temperature of the system, and you get the moles from here, and then you can calculate the volume. Dalton's law of partial pressure is fairly simple, and this is one that cannot be derived from the ideal gas equation. And the simplest way I like to say is the total pressure just simply added to the individual pressures. And ultimately what you can say is that if you have atmospheric pressure as 1 atmosphere, right, at sea level, and the atmosphere is 78% nitrogen and 21% oxygen, we can define a percentage or a fraction of that. That fraction is equivalent to the fractional pressure, which means at atmospheric pressure, the pressure of nitrogen will be 0.78 atmospheres, and oxygen will be 0.21 atmospheres because that's the percentage of the gas that it represents. So it represents a percentage of the pressure. Diffusion and effusion, I need to distinguish between those. You do not have to know this mathematically, just conceptually, that the heavier the gas, the slower the diffusion or the effusion. That's why it's inversely related, right? You got it, the square root of the molar mass. Effusion is moving through a hole. Gas is moving through a hole, like escaping from a balloon. Diffusion is just spreading out. So that's the difference between those two. But basically, we apply the same laws, and we'll talk about that a little bit, not much in class. But that concludes the video. Be sure to watch it before class lecture.